Hi, this is Professor Fernandez. In this video, we're working through example 4.16 from the book Calculus Simplified. In this example, it says use the limit comparison test to investigate the convergence of each series. So I've pasted that down here. This is theorem 4.12 in the book. Let's review it really quickly. Suppose AN and BN are two series that all have positive terms, right? So that's the limit comparison test restriction. Another if, so suppose that when I take the limit of the ratio of these AN and BNs, I get some number that is finite and positive. Okay, then both series either converge or they both diverge. Great. So translation, takeaway, if I have two series that only have positive terms, and when I look at the ratio of those terms, the limit is some finite number, then they both converge or they both diverge. Great. So to use this test in practice, right, we have to do this verification, all the ifs. But really, what does it boil down to? Well, you need to know, let's say that one series converges or diverges. Because if you are able to verify all these other things, then the test tells you the other series also converges or diverges, right? So that's why it's called the comparison test. You take a limit, you take a series that you already know converges or diverges, and you compare it in this fashion. And if the test hypotheses are met, then that tells you the other series converges or diverges. Okay, so let's go through the examples over here and see how this works in practice. Let's take a look at the first example here. Like all the series that you've probably heard from me saying from these videos, you want to get a sense of whether a series converges or diverges first before you go off and try to show it using a test. 1 over 2 to the n plus 1, well, 2 to the n is exponential, exponentially growing, and if I add 1, it doesn't really change much, right? If you imagine n being like a trillion, 2 to the trillion plus 1 is pretty much 2 to the trillion. So we get a sense that this series, the terms, start looking more and more like 1 over 2 to the n as n gets really large. And actually what I just did is exactly what I suggest you do to come up with this other series you need for the test that you're going to compare the original series to. Now, it doesn't matter which series is AN or BN, right? So I like to just keep things simple and let AN be the original series, BN be the series that you get from thinking about this convergence question early on. So now we go off and we start verifying all the test hypotheses. First of all, we need to figure out if all the terms in these series are positive. Indeed they are, right? 2 to the n, exponentially growing, never 0, much less negative, so always positive. I add 1, always positive. I take the reciprocal, always positive. And then same deal over here, so check. Number 2, now I'm going to take the limit as n goes to infinity of an divided by bn. Right? It doesn't really matter if you do bn divided by an, right? It's totally up to you. So let's just put in what an and bn are here. So an is 1 over 2 to the n plus 1, and then I'm going to divide by bn, which is 1 over 2 to the n. Okay, remember that when you divide, it's the same as multiplying by the reciprocal. So 2 to the n over 1. So in this case, we have the limit of 2 to the n over 2 to the n plus 1. And various ways to argue what this limit equals, but we can reason it out as follows. Again, as n gets larger, the denominator starts looking more like just 2 to the n. The plus 1 really doesn't change the y value by much. The numerator remains 2 to the n. So what I'm doing here is using something called a growth argument. I'm trying to understand how the terms, how the expressions in this quotient grow as n gets larger. And I've just determined that the denominator grows eventually just as fast as the numerator. So this limit, this function, tends to 1 in the limit as n goes to infinity. 1 is definitely bigger than 0, right? And it's definitely finite. So I've checked the second requirement here for the limit comparison test. Okay, the last one is to know whether the bn series that I'm using converges or diverges. Okay, so in this case, if bn is 1 over 2 to the n, and this series starts at n equals 0, doesn't really matter so much because this is 1/2 to the n. and therefore it's a geometric series with r equals 1/2. We know that the convergence condition for geometric series is that r is less than 1. In this case it is, it's 1/2. So actually this series converges. So the limit comparison test tells me, hey, I have verified all three requirements of the test, and I now know the series I'm comparing my original one to converges. So the limit comparison test tells me, hey, so does the series you're looking at. That one converges too. Great. Okay, so I'm going to make myself give myself some space here so we can work on part B. Let's take a look at that one. So that one says, what if I look at this series? No longer has exponential functions. That's a bunch of, functions, algebraic functions, n to a power. Same deal, right, as before. So let's take this expression and ask ourselves, what happens as n gets really big, right? As n gets really big, the +1 doesn't matter so much. So the series is eventually going to look closer and closer to this. And over here, I can simplify this. This is n to the 1/2 over n squared. Rules of exponents, that's n to the 1/2 minus 2, which is n to the 1/2 minus 4 over 2. And so that's n to the negative 3/2. Rules of exponents again, that's 1 over n to the 3/2. Rules of exponents one last time, which is 1 over the square root of n cubed. I can keep going from there, right? But actually, I'm going to back it up to here because now, eventually, we are going to use the fact that the series I'm comparing to is a p-series. So we'll do that in a minute, but we've just shown that when n is large, this series looks very close to that series. So again, I'm going to call this my a sub n, call this my b sub n, and run through my checks. Is an or are an and bn positive? They are. There's no subtraction here. All the n's are positive, and I'm adding 1, right? So everything is good to go. Number 2, I'm going to look at the limit as n goes to infinity of an, which is this, divided by bn, which is my other series. Okay, again, multiplication by the reciprocal, so multiplied by n to the 3/2 over 1. And then over here, n to the square root of n, I'm going to write that as n to the 1/2. Okay, great. And then I'm looking here to do some simplification. In the numerator, I have n to the 1/2 times n to the 3/2. Rules of exponents, same base, add the exponents. So 1/2 plus 3/2, that's 4/2, which is 2. So that's my new numerator, n squared, divided by n squared plus 1. Great. And then here, same growth argument, right? As n gets larger, this plus 1 gets more and more inconsequential. I'll have like a gazillion plus 1, pretty much a gazillion. So this limit tends to the same value as the limit of n squared over n squared. In other words, dropping the plus 1, which is once again 1. And back again to the requirements, same arrow here, that is positive, that is finite. So my second condition for the limit comparison test holds. Great. For my third condition, then I now need to figure out, what do I know about this series? Again, it doesn't matter so much where the series starts, happens to start at 1 here. What do I know about the series? Well, this is a p-series with p equals 3/2. Remember that those series look like this. And because p is equal to 3/2, which is bigger than 1, then I know that this series converges, right? So that's our p-series convergence theorem. So limit comparison test tells me, hey, the series Bn that you are comparing your original series to converges. Therefore, your original series also converges. Awesome. So that is it for part B. And then we go on to the last example here, which, part 2 here looks kind of involved, right? But we will see in a minute that by using the techniques that we've been talking about, we can take this example and effectively analyze it in the same way that we just did part B. So let's go off and do that. A lot of stuff going on here, right? But let's start doing what we did before. Start dropping terms as we think about what happens when n gets large. So we'll start in the denominator. oh, that's n cubed, will start in the denominator, right? So as n gets large, think of n like a trillion, a quadrillion or something. N cubed is really, really big, right? It's the cube of that. Compared to 7 times that, it's like no comparison, right? A trillion cubed compared to 7 trillion, there's no comparison. So we can safely drop the n, the 7n, and retain only the n cubed. Numerator, same thing. A trillion squared is much bigger than a trillion, and a trillion is much, much bigger than 1. So I can just drop the n and the 1. Okay, that gets me to here. And n squared over n cubed, that I can simplify pretty straightforwardly to 1 over n. So this is the series that I'm going to use to compare things to, right? Bn, and this one is an. And so let me run through my checks, right? An positive, Bn positive. Yes, once again, everything's being added, everything's being squared. N is a positive number, right? Starts at 1, so everything is good. Number 2, what if I take the limit of an over bn? Well, let's investigate that, right? So here's an, n cubed plus 7n, divided by bn, 1 over n. So once again, multiplying by the reciprocal. So we're going to have a times n over 1 over here. And then I can do some cancellations, right? So what are my cancellations? Well, if I look at this denominator, this is n cubed plus 7, factor out an n, get an n squared plus 7. Okay, so that's my denominator. And this n is going to cancel with that n. So what I'm left with is limit as n goes to infinity of the numerator, n squared plus n plus 1, divided by what was left, n squared plus 7. Now, if I look at this function, same deal. Use my growth argument. As n gets really, really large, it's going off to infinity. Think of n being a trillion again, right? N squared plus 7, only the 7 survives, right? This is going to be the dominant term later. As n goes to infinity, what about this n? Well, compared to the 1, the 1 is insignificant, but the n itself, compared to the n squared, the n becomes insignificant eventually. So again, we get a limit of 1, which is positive and is finite. So yes, the second requirement for our limit comparison test holds. And then number 3, let's look at the series that we are comparing to. And here is starting at 1, goes off to infinity. We've seen this series before. This is the harmonic series. And because it's the harmonic series, it's a p-series with p equals 1, which tells us that the series diverges. Limit comparison test says, okay, since the series you are comparing to diverges, you have verified all the other requirements of the theorem, then the original series you're looking at also diverges. Great. See you next time.